Welcome to video 8, and this is section 4.9 of your textbook. We'll be talking about deferred annuities, and really when we talk about deferred annuities, we could be talking about any sort of set of deferred cash flows, and that is cash flows, in this particular case, uniform cash flows that don't begin immediately. They may begin at some point in the future, and how do we handle those? That's what we'll address in the video today. There'll be some quizzes coming. You need to have watched this video before the quizzes come. And of course, if you take the quizzes ahead of time, before you see the video, you'll understand why when I talk about these deferred annuities. They'll be popping up on quiz 1 a little bit, and they're really not that difficult to handle, but they do require some thought about timing of cash flows. Very important thing to consider. And I will be moving a little more quickly now. You should be familiar and comfortable with the Excel functions that we've discussed so far, the spreadsheet functions we've discussed so far. So I'll move a little bit more quickly when I solve the problems here. You may need to watch it a couple times if you're a little bit confused yet about some of those functions. But please, if you're confused, I know that there are Excel tutorial videos through lynda.com that you have access to through the Virginia Tech portal that goes through all of these functions and the use of those at some level. And also, Missy and I are happy to answer any questions you have. So let's get to the worksheet we'll work on today. This will be posted along with the videos, so you can kind of follow along with the developments as I work through them. So here we go. Let me pull up the spreadsheet for you. And there it is. You can see the title is Deferred Annuities. Cash flows that do not begin immediately but are delayed in time and begin at a point farther in the future than one period. And here's an example. We're going to solve this using an interest rate of 8%. The question that's asked is, what is the present value? And typically when we talk about present value, we're talking about time 0 of this set of cash flows. However, we will discover today that a present value can be just about any place, and as I mentioned in a previous video, these cash flows are all relative. So present is relative to future cash flows, and the future is relative to present cash flows. So here we go. We have cash flows here. Whoops. We have cash flows here that don't begin until the end of year 4. Remember, all of our cash flows are end of year cash flows. And here we have a uniform series. So it's $750 each year, years 4 through 9. And I want to say a little bit something here about a number of cash flows. You know, we're used to finding how many cash flows there are. We're used to doing something like 9 minus 4 would be 5. But remember, when you take 9 minus 4, you're missing the one that's at 4. So the correct calculation would be 9 minus 4 plus 1, because 9 minus 4 is 5 plus 1 is 6. There are 6 cash flows. The way I think of it is I just take 9 minus 3. 3 is the last year in which there is not a cash flow. And that would also give us a uniform series of 6 cash flows. So there are 3 steps, as you can see, in solving these. Step 2 is a bit, not really a calculation step, but a thought step. Let's go through these one step at a time and see how we do. First of all, let's get the information we have. A is equal to $750. The interest rate is 8%. N, let me see, what is N in this problem? Well, for this first step, N is equal to the number of uniform cash flows. So N would be 6. We're not worried right now about the fact that this goes from time 0 all the way through the end of year 9. We're only concerned about one step at a time, and that means that the N is the number of uniform cash flows in the series. So now we need to find P, the present value. You should be able to do that now quite easily. And since we're trying to find the present value, this is not one of those payment things that the spreadsheets are built for. We just want to take the $750 uniform series and we want to squeeze all that up together and represent it by one economically equivalent cash flow. And we do that by solving for P. We'll use the PV function minus PV. And the first argument is the interest rate, 8%. The second argument is the number of years, 6, or the number of uniform cash flows, or 6 of those. The third argument in the PV function is the annual uniform cash flow, and that's $750 here. There are more arguments in the PV function, but we don't need those, so I will just close that out, and we'll see what the present value is. $3,467.16. So that number is economically equivalent to the uniform series of $750, begins at the end of year 4 and continues through the end of year 9. The question is, where is it? This is a P, but it is at time what? Well, it's not at time 0. So this P is not at time 0. Remember the relationship between P and A. P is always one period prior to the first A. So this P is one period prior to the first A, so that puts it at 3. So this P is at time 3. Okay. Now, we wanted to find the present value at time 0 of this set of cash flows. Okay? We now have one economically equivalent amount, and it's at time 3. We need an economically equivalent amount at time 0. How do we do that? How do we do that? Whoops, sorry. Well, P at time 0. How do we solve for that? Well, we have one value now. We can essentially forget about the $750. It's gone. It's been converted into this one single cash flow at the end of year 3, and we need to move that cash flow at the end of year 3 back to the end of year 0, back to the present. That is back 3 years. So I'm going to take that value at the end of time 3, and I will move it back 1, 2, 3 periods, or 3 years, back to time 0. So for this problem, the P is essentially now an F relative to the present at time 0. So I need to find a present value given a future value. This is essentially a P given F, 8% for 3 years. That's what I'm working on here. And let's just use the PV function. minus PV, and the interest rate. The number of years back is going to be 3 years, year 3 to year 0. The next argument is a uniform cash flow. We don't have that. This is not a periodic cash flow. It's a one-time cash flow. So I'll skip that argument. The next argument is the future value. Well, the future value here is the 3467.16, and that's all I need. So the present value at time 0 is 2752.34. So in summary, for this problem, we have converted these 6 uniform cash flows of $750, beginning at the end of year 4, continuing through the end of year 9, to an economically equivalent single cash flow at time 0 of 2752.34. So that's it. We've reduced the picture, if you will, and we've taken it down to a single representative economically equivalent cash flow at time 0, 2752.34. Okay, that's the essence of deferred annuities. We just have to know we find a present value, and we need to know then we move that present value to a different location after we were finished. You know, with these problems, there are always multiple ways to find the right answer. What I showed you right here was one way to find the right answer. Another way would have been to find the future value of these annuities, and then we would take that value, wherever it falls, back to time 0. I'm going to do that very quickly, and I'm going to take, there's our data right there. Let's find the future value. And the future value would be equal to minus FV, interest, number of cash flows. The next argument is the amount, $750. $5,501.95. Now we've taken the 750, the 6 of those, and we have changed those, converted those into an economically equivalent amount at some time. The question now is where? At time what? Well, remember the relationship between F and A. The relationship is the F occurs at exactly the same time as the last A. So this is at year 9, the end of year 9. So I have a single cash flow at the end of year 9, and I want to find P of 0. I'd like to find that. How would I do it? Well, I would take this single cash flow at the end of year 9, and I would bring it to the present with a present value, right? And this would be a P given F. This would be just like this guy, P given F, 8%, but the years now would be 9 instead of 3 over here. So let's do it with 9 and see what we get. Equal negative PV, interest, years, 9. The next argument is a uniform series. We don't have that. We just have a single cash flow, a single future cash flow. There we go. Son of a gun, exactly the same answer, 2752.34. So it really didn't matter whether we took that uniform series to the present or took the uniform series to the future. The concept is the same. We gather all those up, find an economically equivalent amount somewhere, And then we take that one single economically equivalent amount somewhere and we move it back to time 0. As a matter of fact, if I had taken this 5501.95 back to time 3 instead of time 0, so I had done a P given F 8% for 6 periods, that would be 9 minus 3, or 6 periods, I would have found 3467.16. So once again, just to demonstrate, these are all economically equivalent. They just happen to be occurring at different points in time. Let's look at a little more complicated problem. Look at the cash flows here and find the future worth at time 12. And we're going to let the interest rate be 6%. There we have it. Here's the complicated cash flows. We have negative 9,000 at time 0. We have a uniform series, end of years 3 through 7. And we have 12,000, a positive 12,000 at the end of year 9. And we want to find the future value at time 12. We have 3 separate cash flows to consider, 3 separate sets of cash flows. We have the negative 9,000, we have the uniform series, and we have the 12,000. And we can take each one of those to the end of year 12. So let's first look at the initial time 0 cash flow. And the $9,000 cash flow is a negative $9,000. I can move that directly to the end of year 12. I'm going to do that equal FV, future value, negative FV, future value, and the interest rate is 0.06, 6%. The number of years is 12. I'm taking it from time 0 to time 12. And the next argument is a uniform series, which I'm not working with right now. It's a single cash flow, so I'll skip that argument. Now the single cash flow, a present value, negative $9,000. And there we have it. And so that economically equivalent amount at the end of year 12 is negative $18,109.77. I'm going to change the format of that to my favorite red format there. So there we have this. This is the economically equivalent amount at the end of year 12 of this guy right here. I will throw in right here, and if this seems confusing, don't worry about it. There's a question that we'll be asking on the homework. The rule of 72. And here's the rule of 72. If I take the number of years times the interest rate, when that is approximately equal to 72, which it is here, 12 times 6, 72, that indicates a doubling of money, 9,000 to 18,000. That's really close. So this is, so you should be able to eyeball this and say, that looks about right. It should be, if it's 12 years and 6%, it should be about twice what the original value was. And it is. So that represents the equivalent amount for the negative 9,000. Now let's do the uniform series just like we did before. We could either do the present value of those, or we could do the future value of those. I don't care, and it doesn't matter which way we do that. It will give us the same answer either way. So I'm going to here just find the present value of those, of that uniform series of cash flows, equal negative PV, 6%. How many cash flows are there? There are 5. 1, 2, 3, 4, 5. And the next argument is that uniform series. 4,000 is how much the uniform series is. I'll just pick the first one to get a number. And there we go. $16,849.46. Okay, now, however, that, remember, is where in time. We found the present value So this is 1 year prior to the first A, so this is at end of year 2. We need to take that to year 12. So that's now a single economically equivalent amount to these, but it's at the end of year 2, so I need to take that forward 10 years. So this would be a present amount. I need to find the future amount, equal negative FV, interest rate 6%. How many years? 10 years, from the end of year 2 to the end of year 12. The next argument is that uniform series, which we've already gotten rid of. We're working with a single amount here. So I'll skip that argument. And here we have the single amount at the end of year 2. And there we have it. This is the economically equivalent amount at the end of year 12 of this series of cash flows of $4,000, end of year 3 through end of year 7. Okay. What's next? It's this last one. It's a single cash flow that occurs at the end of year 9. So I need to take that forward 3 years. I just need to move that ahead 3 years. And there's, we can do FV equal minus FV, 6%. We're moving it from 9 to 12. That's 3 periods. We have, there's no uniform cash flow here. We're looking at a single value, and that value is $12,000. We move that forward, and it's 14,292.19. Just because I need to get it off my chest, when I'm using present or future, I will quite often just use the formula as opposed to using the Excel functions or the spreadsheet functions. I'm not sure why I do. That's just the way I roll. So another way we could do this is that it would be equal to this number times 1 plus I to the n, 1.06 cubed, and you'll get the same answer. If you don't like doing that, don't worry about it. That's just a quirk I have. So we've moved each one of these sets, the negative 9,000, the 4,000 series, and the 12,000 single amount. We've moved each one of those to the end of year 12. Now that each one is at the same point in time, I can add them. I couldn't have added them before, but now each one occurs at the same time, so I can add them up. So the future amount I'm interested in is the negative 18,110 plus the 3174 plus the 14,292, and there we have it. If we look at this set of cash flows, the economically equivalent amount at the end of year 12 is $26,357. So 3 steps there for each one, and then add them up to find the actual economically equivalent amount at the end of year 12. And that's it. That's deferred annuities and moving the cash flows around. So you need to, if you're not there yet, you need to work on being very comfortable just with moving cash flows from one place to the other, to the other, to the other, and comfortable with using the spreadsheet functions. If you are comfortable with that, I know that the work will go quickly and it will go smoothly. You just have to be cautious and pay attention to detail, the timing of these cash flows, when they happen. So you take them to the proper place is very critical, and you can't do it in a slipshod manner. It's not hard, but it's details, and it's repetition and going through step after step after step. The next section in the textbook, 410, is a section that we don't cover. It's not that it's unimportant. It's just that with what we need to get accomplished. We don't have time to spend another few minutes and some problems on it. And this is where interest rates change with time. So the interest rate in the first period may be different than the interest rate in the second period, different than the interest rate in the third period. And the bottom line on this sort of problems is that you really just have to brute force your way through it. That's just the way it is. So, but we're not going to cover it. You will not be held accountable. I won't ask any questions about it, either on the homework or on the quiz or anything like that. We will move to the next section, which I believe is 411, and that's gradients. So video number 9 coming up will be a video on gradients, where cash flows change over time according to either a constant amount or a constant rate, and we'll cover that when we get there. So I'll see you on the next video.